Imagine taking two massive cylinders of steel, right? And you press them together with hundreds of thousands of pounds of force.
Yeah, and then you just spin them.
Exactly. You spin them until they permanently weld themselves together just by their own friction.
Which is, a multi-million-dollar disaster waiting to happen.
Right. And today, for our deep dive, we are looking at the microscopic analog technology designed to stop exactly that.
Yeah, it's a fascinating topic.
We have a source document in front of us that, well, at first glance, it might seem incredibly niche to anyone outside the industry.
Oh, definitely. It looks like standard paperwork.
Right. It's a product data sheet for an industrial compound, specifically the JetLube KOPR-KOTE drill collar and tool joint compound.
I mean, it sounds like a catalog entry, but it is actually a blueprint for surviving some of the most hostile environments on the planet.
Yeah.
Oh, yeah. We are talking about operating conditions that, frankly, fundamentally break standard physics and chemistry.
Well, our mission today is to decode this document. We want to uncover the fascinating science of how colossal drilling operations prevent catastrophic mechanical failures.
Using a very specific, carefully engineered paste.
Exactly. And to set the stage for you listening, try to picture the sheer scale. We're talking about drill collars, cool joints, and entire drill strings plunging miles deep into the earth.
Yeah, the scale is hard to wrap your head around.
They are operating under immense heat, crushing pressure, and with staggering compressive forces. They're rotating, grinding, and bearing the weight of all the steel above them.
And all of that steel has to be connected somehow, right?
Right.
The source notes that copper coat is applied to the oil field threads on those drill collars, tool joints, and drill strings.
So it's right there at the connection point.
Exactly. It conforms with API RP 5A3, which is the industry standard for use with rotary shouldered connections.
I see.
You have these separate 30-foot sections of really heavy pipe, and they must be screwed together to form a drill string that might be, 2 miles long.
So we have all these threaded pieces of pipe screwed together, and they're spinning under unimaginable torque.
Yeah.
Now, the datasheet points out a very specific threat that KOPR-KOTE is meticulously crafted to counteract.
Right, the excessive makeup.
Yes, the exact term used here is excessive circumferential makeup, which the document says leads to seizing and galling.
It's quite the phrase.
It really is. Let's translate this industrial jargon. What exactly is going on down there?
Well, think about the rotational force of the drilling itself. The machinery on the surface is spinning the entire pipe string to cut into the rock, right?
Okay, yeah.
And makeup simply refers to the tightening of the threaded connection between two pieces of pipe.
Right.
So the downhole forces naturally want to keep tightening those threads as the drill spins.
Oh, I see.
Yeah, excessive circumferential makeup means the threads are, well, they're continuing to tighten far beyond what the engineers designed them to handle.
Is this basically like, when you screw a jar lid on way too tight and the threads get eternally stuck? But like scaled up to thousands of pounds of steel.
The jar lid analogy captures the frustration, definitely. But the physical reality of steel under that much torque is far more violent.
How so?
If you look at steel under a microscope, it isn't perfectly smooth. It looks like a jagged mountain range.
Oh, wow. Okay.
Yeah. And when you force those microscopic mountains together under extreme weight and rotation, the friction generates so much localized heat that the peaks of the metal actually melt and fuse together.
Wait, really? They actually melt?
They do. And as the rotation continues, those welded peaks are violently torn apart, which leaves gouges.
Yeah.
And then the whole process repeats just a millimeter later.
That sounds incredibly destructive.
It is. That is galling. It's essentially cold welding and then ripping the metal apart simultaneously.
If that happens 2 miles underground, you suddenly have a massive section of pipe permanently locked together.
Exactly. Or the threads are completely destroyed. The structural integrity is just gone.
Right.
You might not be able to pull the pipe out. Or worse, the string snaps downhole.
So that is why the datasheet highlights that KOPR-KOTE's primary job is the preservation of joint efficiency.
Yes, exactly. It has to enable the seamless mating of joint shoulder faces without any standoffs or deformation.
The joint must meet perfectly, bear the load, and never deform from being crushed together.
Right?
Okay, let's unpack this, because this brings us to the formulation and, frankly, a bit of a paradox.
Oh, yeah.
According to the source, this is a lead-free and zinc-free formulation. It incorporates copper flake, graphite, and natural extreme pressure and anti-wear additive.
Right.
And all of this is held in an aluminum complex grease base. But here's where I need you to unpack things for us.
Sure.
A grease, by definition, is supposed to be slippery, right? Its whole job is to reduce friction so things can slide.
Yeah, generally speaking.
But the datasheet explicitly says copper-coated counteracts excessive makeup by enhancing the coefficient of friction when subjected to compressive forces.
Yes, it does.
How does a friction-enhancing grease make any sense?
What's fascinating here is that it seems completely contradictory until you look at the mechanics of what they call the unique solids package.
Okay, the unique solids package.
Right. Copper coat is not a static liquid. It is a dynamic material. The copper flakes and the graphite are suspended in that grease base.
Right.
And under light pressure, like when the crew is first screwing the pipes together on the rig floor, the oil and grease do act as a traditional lubricant.
So the pipes thread together smoothly at first.
Exactly. But as the drill pipe lowers into the hole and the rotational torque and compressive stress levels skyrocket, the environment changes.
Oh, so?
Well, the oil gets squeezed out of the microscopic spaces between the steel threads.
Oh, I see.
Suddenly, those copper flakes and graphite particles are the only thing standing between the two steel surfaces.
So think of those copper flakes like microscopic speed bumps.
Yes, great analogy.
Under light pressure, the fluid lets you slide right over them. But when the pressure skyrockets, the fluid is pushed aside, and those tiny copper speed bumps lock together physically.
Exactly. That physical locking is what restricts the downhole makeup. The friction factor actually increases in direct response to the rising stress.
That's brilliant.
It really is. When the joint reaches its ideal tightness, the compound stops acting like a lubricant and transforms into a physical barrier.
It says no further.
Exactly. It physically stops the drill joints from over-tightening.
It's essentially a material that knows when to stop being slippery.
Yeah, that's one way to look at it.
Now that we understand how this dynamic barrier works, let's talk about the nightmare conditions it has to survive.
Oh, the environment is brutal.
The datasheet has a section called Typical Characteristics, and the numbers are just intense. For instance, it uses a complex soap thickener.
Right.
Now, whenever I hear soap, I think of washing my hands, which doesn't seem like something you want inside a drill pipe.
Well, in chemical engineering, soap has a very different meaning.
Okay.
A lubricating grease is essentially a sponge holding oil. The soap is that sponge. It's a thickener matrix made from metallic compounds.
Like the aluminum complex soap mentioned here.
Exactly. Its job is to hold on to the oil, the copper, and the graphite. It keeps them all evenly distributed until the pressure forces them into action.
And that sponge has to survive insane temperatures.
Oh, definitely.
The datasheet lists a dropping point of 450 degrees Fahrenheit, or 232 degrees Celsius, and a flash point of over 430 degrees Fahrenheit.
Right.
What is the practical difference between those two numbers for a rig operator?
Well, the dropping point is the temperature at which that soap sponge breaks down and the grease liquefies.
What?
It literally turns into a liquid that drops away.
Oh, wow. Not good.
No, not at all. And the flash point is the temperature at which the vapors off the compound could actually ignite if exposed to an ignition source.
That sounds dangerous.
It is. When you drill deep into the Earth's crust, ambient temperatures soar, and the friction of the bit itself generates massive heat.
Right.
If your thread compound melts away into a puddle, you lose your copper speed bumps, and you instantly get galling.
And a major headache.
Exactly.
So the service rating spans from a freezing 0 degrees Fahrenheit all the way up to 450 degrees.
Yeah, it's quite a range.
Moving from heat to sheer weight, the sheet mentions an 800-kilogram force 4-ball weld point.
Right, the 4-ball weld test.
I assume this involves steel balls, but how does a soft paste stop raw steel from fusing under almost a ton of concentrated pressure?
It's a brutal industry standard. They take 3 steel balls, clamp them together in a triangle, put a 4th ball on top, and spin it while applying increasing mechanical load.
Okay.
Without protection, the friction and pressure cause the metal to instantly gall and weld solid.
But copper coat survives that.
It survives up to 800 kilograms of force on that tiny microscopic contact point.
That is wild.
Yeah, the extreme pressure additives in the compound activate under that heat and pressure. They form a sacrificial chemical film on the metal.
So the film takes the damage, so the steel doesn't have to.
Exactly.
That explains the durability. Let's look at the physical consistency. It has a specific gravity of 1.15, meaning it's heavier than water. And it has a density of 9.6 pounds per gallon and an NLGI grade of 1.
Yeah.
What does an NLGI grade 1 actually feel like in the hands of a rig worker?
Well, the NLGI scale measures the stiffness of a grease. A 0 is almost fluid, like a heavy syrup.
Okay.
And a 3 is very stiff, like a solid block of butter. Grade 1 is roughly the consistency of tomato paste or mustard.
Got it.
It is soft enough to be easily brushed onto massive steel threads by a worker on a freezing rig floor, but dense enough that it won't just slump and run off the pipe before they can screw it together.
Here's where it gets really interesting. That perfectly sets up what I think is the most remarkable operational stat on this whole sheet.
Oh, the wet joints.
Yes. It specifically highlights that the compound sticks to wet joints, and there's also an Arctic grade available.
Right.
If you're pulling a pipe out of a hole, it's covered in mud, water, and who knows what else.
Exactly. Having to completely dry and clean every single massive thread before applying new compound would bring a multi-million-dollar operation to a complete standstill.
And time is literally money on a rig.
Precisely. Because the specific gravity is heavier than water, and because of the properties of that aluminum complex soap, the compound physically displaces the water.
So you can just brush it right onto a wet pipe?
Yep, and it will cling directly to the steel.
The document also explicitly states it is approved by NAMSHEL for underbalanced drilling applications.
Yes, that's a big deal.
Underbalanced sounds like something you don't want your drill to be. Why is this approval so important?
Well, in traditional drilling, operators pump a column of extremely heavy fluid down the hole. This holds back the immense pressure of the oil or gas in the rock formation.
Right.
The pressure of the fluid is greater than the pressure of the earth, keeping it balanced or overbalanced.
Okay, so what is underbalanced?
In underbalanced drilling, the operator deliberately keeps the pressure inside the wellbore lower than the surrounding rock.
Wait, why would they do that?
It allows oil and gas to flow to the surface while drilling, which can be great for production, but it is highly volatile. The margins for error are non-existent.
Because the risk of a blowout is higher.
Exactly. Having a compound certified for that environment means major operators trust it not to fail when the wellbore is live and unpredictable.
Wow. So we have a dense, water-displacing, heat-resistant paste that physically fights back against over-tightening?
Yeah, that sums it up nicely.
But how do the engineers on the rig actually apply this science? They can't just slap it on and guess.
No, absolutely not.
The data sheet introduces very specific math regarding the friction factor. For KOPR-KOTE, it is 1.15 relative to APIRP 5A3 Annex 1.
Right.
The instructions say that for optimum performance on API drill string connections, operators must take the pipe manufacturer's recommended torque and multiply it by 1.15.
Yeah.
Walk us through the mechanics of that.
This goes right back to your speed bump analogy. The equipment manufacturer calculates a baseline torque for how hard a machine should twist two pipes together.
Okay.
And that assumes a baseline friction factor of 1.0. But remember, KOPR-KOTE enhances the coefficient of friction under pressure.
Right. The copper and graphite are actively resisting the spin to protect the threads.
Exactly that. So the rig's machinery has to fight through that deliberate protective resistance.
You have to push 15% harder than the baseline just to overcome the compound's protective barrier.
Right, to get the joint to perfectly seat. The source notes these friction factors were developed using full-scale API tool joint connections.
So the 1.15 multiplier isn't just a suggestion.
Not at all. It is a mathematically tested requirement to ensure the connection is tight enough to hold, but protected enough not to gall.
But engineering is never one size fits all, and the data sheet actually proves that by listing several alternative products for scenarios where KOPR-KOTE is the wrong tool for the job.
Yeah, there are always exceptions.
Let's explore these because they really highlight how delicate the chemistry of a drill site is. First, it says if you need a 1.0 friction factor, you use JetLube KOPR-KOTE FF 1.0.
Right. Some automated rig setups or specific engineering protocols are locked into a 1.0 friction model.
I see.
They cannot safely alter the machine's torque settings by 15%. So the chemists reformulate the compound to remove that extra resistance while trying to maintain as much of the protective solid barrier as possible.
The source also mentions premium connections. It lists brands like High Torque Q, Extreme Torque, and XTM.
Yeah, those are highly specialized.
It says these utilize makeup torques based on a 1.0 friction factor, so you must use the torque provided by the manufacturer. Why do premium threads change the rules?
Standard API threads rely on the face of the pipe joint and the grease to handle a lot of the structural load. Premium connections, on the other hand, feature highly complex proprietary thread geometries.
Okay.
The physical shape of the metal is engineered to provide its own locking mechanism and fluid seal.
So the metal is doing all the structural work.
Exactly. Adding a 1.15 friction-enhancing compound would completely throw off the intricate physics of that connection. You could severely damage those specialized threads by applying the wrong torque multiplier.
That makes sense. The datasheet also mentions another exception. For wedge-type thread connections, NCS 30 ECF is the ideal choice.
Yes, wedge threads are another beast entirely, and they require a specific formula to seat properly without galling.
And the environment inside the hole changes things, too. The datasheet warns that for invert or high pH muds, operators should use a product called JetLube Extreme.
Right.
Why would the mud force you to switch out your thread compound?
Drilling mud isn't just dirty water. It is a highly engineered chemical cocktail used to cool the bit and bring rock cuttings to the surface.
And high pH muds are highly alkaline, right?
Exactly. If you remember our discussion about the aluminum complex soap acting as a sponge for the grease, alkalinity attacks that specific chemical structure.
Oh, no.
Yeah, a high pH mud will actually break down the chemical bonds of the KOPR-KOTE sponge through a process called saponification.
Wait, it literally turns it back into soap.
In a way, yes. It tunes your heavy-duty protective paste into a useless, runny liquid. JetLube Extreme uses an entirely different base chemistry designed to survive alkaline environments.
It's a massive puzzle. You have to match the thread geometry, the torque math, and the chemical pH of the mud perfectly.
It's incredibly complex.
Speaking of matching the environment, that brings us to the environmental credentials on this sheet. We're talking about tons of industrial grease being plunged into the earth or offshore waters.
If we connect this to the bigger picture, it is a critical aspect of modern drilling.
Yeah.
Historically, the best way to get extreme pressure protection, that 800-kilogram force weld resistance we talked about, was to load the grease with heavy metals, specifically lead and zinc.
Which are ecological nightmares if they leach into the water table or the ocean.
They are toxic, and they persist in the environment practically forever.
Right.
The engineering achievement of KOPR-KOTE, as noted in the source, is that it is a lead-free and zinc-free formulation.
Oh.
By utilizing that specific blend of copper flake, graphite, and natural additives, they achieve the necessary extreme pressure barrier without the toxic heavy metals.
The sheet explicitly highlights this, actually. It says it is not classified as a marine pollutant under DOT approval CA 2004-08-25.
Right.
And it holds a CFS OCNS Group B environmental rating in the United Kingdom, which governs offshore chemical use.
Yeah, exactly.
So they are achieving this brutal industrial performance while keeping the heavy metals out of the biosphere.
It proves that industrial power and chemical responsibility don't have to be mutually exclusive if the engineering is rigorous enough.
So what does this all mean?
Well,
For you listening, the next time you see footage of an oil rig, a massive bridge construction, or any colossal industrial project, it might just look like a monument to raw power. Giant diesel engines, spinning steel, brute force.
yeah, that's what usually grabs the attention.
But keeping that colossus running relies entirely on the invisible. It relies on a microscopic layer of copper flakes, graphite, and a complex soap matrix.
A paste that clings to wet steel and laughs at 400-degree heat.
And intelligently increases friction under pressure to protect the machinery from destroying itself.
True engineering brilliance often lies in those unglamorous details. The most critical component of a multi-million-dollar drilling operation isn't necessarily the largest engine.
Right.
It might just be the carefully tailored, lead-free anti-seize paste that quietly prevents a disaster 2 miles underground.
It is the silent guardian of the whole operation. And I want to leave you with a final thought to mull over.
Sure.
KOPR-KOTE is, in a very real way, a material that dynamically reacts to physical stress by altering its own properties to protect its host structure.
It gets tougher the harder you push it.
We live in a world obsessed with electronic sensors, digital software, and microchips. But this is an analog, purely chemical smart material.
It really is.
It makes you wonder how many other analog, purely chemical smart materials are out there, hidden in plain sight, calculating forces and reacting without a single line of code, quietly holding our modern infrastructure together.
That's a great question.
Keep that in mind next time you struggle to open a stubborn jar lid. Thanks for joining us on this deep dive.